Hi, I'm Dr. Sarah Jane Potts from Swansea University, and today we're going to look at the science behind the way that fluids work and what makes them really cool and fascinating. And we're going to look at some ones that you can find in your very own home. Let's start with a fluid that makes up over half of our body mass that we use every day to stay hydrated and wash. You guessed it, it's water. Now, water is a simple fluid known as a Newtonian fluid, which means that its viscosity, so how much resistance it has to flow, how much force it takes to flow, it's the same no matter how fast or slow I stir it, or for how long I stir it. But fluids aren't all like this, so let's also look at some non-Newtonian fluids. So here in the bedroom, I've got a couple. Let's start with inks. So something you might use in school to create a really nice painting, or something you might use to paint your walls. So this is a carbon ink that I use in my work as it's conductive. So when I stir it faster and faster, it flows easier and easier. It's the reason that why when we paint our walls, when we put it on the walls, it flows really easily and it's easy to put down. But when we leave it alone, it's not a puddle on the floor. Because at rest, it has a lot of resistance to flow, so it stays pretty much where it is. But when I stir it faster and faster, it becomes easier to flow. Now this material is also something called a viscoelastic. So visco is in a flowing liquid, and elastic like an elastic springy spring or a bouncy ball. So when I pour this ink up, you can see that rather than just drip back into the pot like you'd expect if I was dripping with water, this actually bounces back up towards the brush. So when I bounce up and down, you can actually see it springing and going back up there like a springy spring. Now let's move on to something else that you guys might use at home or when you're making crafts. So that's plasticine. Now plasticine is a different type of fluid called a Bingham fluid, which means that at rest, so when I leave it alone, it has quite a high resistance to flow. So Bingham fluids will have different resistances, which we'll go through today. But this one has really high, which is why at rest, it will stay exactly how it is. But as soon as I start applying enough force, it will flow, allowing me to change its shape easily. When I leave it alone, it's gone into the new shape that I've left it in. Finally, something that you might have at home, play with in school, is silly putty. Now, silly putty is the opposite to inks, because when I apply more force, it becomes harder and harder to make it flow rather than easier and easier. But as with an ink, it's also viscoelastic, which means that when I pull it slowly, it flows like a nice flowing liquid. But when I pull it fast, it will break apart. And then when I make it into a ball and bounce it, it bounces back up like a bouncy ball. But now let's go into the kitchen and see a few more. There are many cool fluids that you can find in the kitchen. So today we're only going to be looking at a few. So let's start with kitchen oil, so things like olive oil. Now as with water, this is Newtonian, so no matter how fast or slow I stir it or for how long I stir it, it will flow exactly the same, with the same resistance. But unlike water, this has a far greater resistance to flow. So when I start to tilt it, it will flow a lot slower than water would, far more resistance. Then, as with the paint, we have things like yogurt. So this is also sheer thinning, which is why when you get it fresh out the pot, it can come out in these big blobs. But then as you stir it faster and faster and faster, it starts to flow more and more like a typical liquid, and it starts to drip from your spoon. On the other hand, as with plasticine, we have some more Bingham plastics. These have a far lower force needed to start to flow. So these are things like ketchup and mayonnaise. So let's look at the ketchup. So when I start squeezing my ketchup, nothing happens until I reach a certain force and it starts to flow. But then what you might see is, as with our inks and our putties, there's also some elasticity to our ketchup. So when we squirt it out, some of it comes snapping right back up towards the bottle. And then on the other end, we have things like potato starch. So as with the putty, this becomes thicker and harder to flow as we apply more force and stir faster and faster. So if I stir this really, really slowly, I can move my chopping stick around there quite comfortably. But then if I take my chopping stick and I stab at the glass, I cannot get my chopping stick through to the bottom. Whereas if I push it in slowly, it can make it all the way down. But if I try and pull it out fast, it's quite a lot of resistance. It's quite hard to pull out. How do these things happen and why? So with things that become easier to flow as you stir it more, we have two things happening. So there are tiny little particles and polymer chains that you will find in your fluid. So in this case, we have our particles and our chains are all coiled up in random places, and our particles are in all these different directions. So when you try and flow slowly, they're going to start bouncing and smashing into one another, which makes it quite hard to flow. But as you go faster and faster, these coils, these little polymer strings, start to stretch out and straighten in a line as our particles also start to align and flow beside each other instead of into each other. It makes it easier and easier to stir as we go faster and faster. On the other hand, we have things like our potato starch and our putties, and these are normally dispersions, so things which contain lots of different types of particles of different sizes. So in our case here, we have all these tiny little water particles with these slightly bigger starch particles, so in this case potato starch. And when they're flowing around slowly, they're just minding their own business and slowly going around. But if you apply force quickly, like I was stabbing there, the water particles can get away, whilst all of the starch ones start to interlock together like a big traffic jam, and which makes them far, far, far more resistive to flow. And now we finish in the bathroom, which we go in every day to keep ourselves clean. And there are a few other fluids in here. So as well as water, which we covered earlier, we also have things like shampoo and conditioner. Now, as with our yogurts and our inks, these are shear thinning. So they will flow easier and easier. The harder we squeeze them, or the faster we pump them. Then we also have a Bingham fluid, in the case of toothpaste, which is why when you squeeze the toothpaste out onto the toothbrush, it doesn't flow until you reach the needed force. So that concludes our session of fascinating fluids around the home. I hope you've learnt some cool science behind why your fluids behave the way they do, and you're interested now to look around your very own home and discover what it has in store. So thank you for listening, and I hope you had a great time.